All right, everybody, good to see you all here. Can you guys all hear me okay way at the back up there? Okay, fine, great. So, welcome back, everybody. I hope you all had a really good weekend. So today we're going to be continuing what we started last week, thinking about electric fields. And specifically what we're going to be focusing on today is what's called Gauss's law. Now, has anybody done Gauss's law before? Or is this going to be something that's new? Okay, so if this is something that's going to be new to you guys, that's absolutely great. So a bit like the last lecture, you're not going to need your calculator for this lecture. All the questions we're going to have today, they're going to be conceptual questions. But again, it's very important, make sure you get the practice in at the workshop with the numerical examples. But if for this lecture we can get a really solid understanding of the principles, of the concepts, that's going to set you guys all up really well. You're going to be able to deal with the numerical questions, no problem. So that's what we're going to be thinking about today. Now, for a bit of a sort of plan, a bit of an outline, going for a bit of a graphical approach today, something a bit different. So by way of a kind of plan for today, I'd like to sort of illustrate it with three different concepts that we've been learning about over the past few weeks. Because what today's all about, it's about bringing these concepts together and understanding them and building a framework that's going to help us to understand all of them. And that's something that I really like about physics in general, and hopefully you guys are going to really like about the lecture today. So we started a few weeks ago, thinking about voltage and potential difference. You guys remember that, with the roller coaster, didn't matter how high the roller coaster was. What mattered was the difference in energy between those 2 points. That's what we're really getting at with voltage. And then we were looking at capacitors, and we had these two metal plates. We could fill them with some insulator, increase the capacitance. And we had that nice equation where if we knew the voltage, we could think about how much charge was being stored on the capacitor. And then last lecture on Friday, we started thinking about electric fields. So if we had a point charge, we saw that there was this electric field, comes out like this, and these lines, they tell us the direction of a positive test charge. So if we take a little test charge here, it's got a positive charge, put it there and let it go, it's going to fly out in the direction of those electric fields. So what we saw last time was a way to build the electric field due to one point charge in space. But very often in physics, in engineering, we don't just have one point charge, we have an interesting distribution of charge, like in a capacitor, that's not just a point charge. And we want to be able to understand the physics and the dynamics of what's going on there. So what today's all about, and which is why I'm kind of so excited about it, is because we're going to be bringing all of these big old concepts together and understanding them with Gauss's law. And Gauss's law is really the picture which allows us to bring all of these concepts together and understand them as a single thing. So hopefully you guys are going to find it interesting today. Now, the place to start thinking about Gauss's law is with a bit of a recap of what we saw last time with these electric fields, when we just have a point charge and there's some electric field. So let's start with just a one slide recap of what we saw last time. Hopefully it should be a bit of a refresher, and also it's going to set us up for thinking about how to generalize it. So last time we were thinking about electric fields, and the thing that we were thinking about specifically is what I'm calling over here radial electric fields, where the electric field, it's spherically symmetric. So we just have one point charge, and the electric field, it's the same in all directions. So whichever direction around that charge you are, the electric field's going to be the same. And that symmetry, that really helps us out, makes our life a lot more straightforward, actually. Now, we saw at the end of last lecture what the electric field for a point charge is. So it looks like this. So this E here, it's E for electric field. So don't confuse that with E for energy. And we saw that it's just equal to the Coulomb constant multiplied by whatever the charge is, divided by the square of the distance that we are from the charge. So that's the electric field for a point charge, and it only depends on how far we are from the charge once we know what the charge is. Now, if someone came along and said, what's the force due to this point charge? What would we need to be able to answer them? Any thoughts about that? Would we be able to tell them what the force is due to this point charge? Any thoughts about this? What do people reckon? Now, it might look like we could tell them what the force is straight away, but if we just went over here to this point charge and someone said, hey, what's the force at this position over here? We wouldn't actually be able to tell them, because remember Coulomb's law from last time, the force depends on the product of two charges. So if we wanted to know the force, we need to know what the charge is on the other thing. So we'd need to know what this little q is. So if we only have one charge, it doesn't really make sense to talk about the force because there's only one charge. We don't know what the force is going to be. If we just put something with no charge, maybe we put a neutron in there, neutron doesn't have any charge, the neutron's not going to see any force. If we want to know what the force is, we need to know what the charge on the thing is. So that's why to get from the field to the force, we need to multiply by whatever the charge is of the thing we're interested in. Or another way of looking at this is, if we know what the force is, we can get back to what the field is. It's just the force per charge. So we only think about the charge of what we've got here. So that's a big part of what we saw last time. Does anybody have any questions about this? Anything they want to ask at this point? So that's the field and the force for a point charge, for a radial field. Now, if we go back to thinking about maybe we've got an imaginary charge over here and we want to move our charge towards this charge, or maybe we want to move it away, we know that there's a force and we know that we're exerting that force over a distance, so we're going to have to do work. So last time we figured out what that work was, and we got that by integrating. So we had to integrate that force over a distance, and this is what we got for the energy. And we just got that by integrating this force with respect to distance. And that's why instead of 1 over r squared, it's just over r there. And just remember, we've got to be a bit careful with the sign of this, whether this is positive or negative, whether we're coming along and having to do the work, or whether we're talking about the work being done by the particle. And if they're equal charges, we're going to have to come in and do the work to push them together. They're not going to want to go together. If they're opposite charges, we're going to have to do the work to pull them apart because they're going to want to stay together. So if we're thinking about the energy, just be careful. Look at the signs of the charges. Just be careful to think about, are we going to have to come in and do the work, or are we going to have to pull them apart, just to make sure you get the sign of that work correct. Now that's a kind of one slide recap of everything that we saw last time, but there's actually a really interesting missing piece of the puzzle. So let's have a think about this. So if we only have one charge, what physical quantity does this thing that I've written down here? So it's the Coulomb constant times the charge divided by the distance, divided by how far we are from the distance. So this is a bit of a tricky one. You might have to have a bit of a chat with the people around you. Think about some of the things we've been studying over the past few weeks. Which one of these concepts does that physical quantity correspond to? If you're not sure about this one, there's that hint there. Think about the energy due to that charge q. So maybe go and look at what the energy is for a charge q. Think about the relationship between that energy, how you'd get from that energy to this quantity here. Maybe that might help you to think which of these physical quantities it corresponds to. Okay, very good to see those responses coming in. Let's see what everybody thinks for this one. What concept does this quantity correspond to? What's everybody think here? Okay, so some people think it would be B, C, or D. Looks like most people going for option A. Now, if we have a look at this concept over here, so KQ over R, that's actually quite similar to that expression we had on the last slide for energy. We're just missing that other Q there. So we've just divided out the energy per charge, which, as looks like most people got, is voltage, okay? So very well done, everybody, with that question, especially if you spotted that this is voltage, because it can be quite counterintuitive. Because, you know, we think of voltage as, you know, that's that thing inside wires, right? And, you know, you can measure voltage with a multimeter, but it's quite strange to think about voltage as being a thing, you know, floating around a charge. So let's see how that fits into our puzzle. See if that can help us figure out what's going on here. So we have, you know, our field, our force, and our energy. And if we look at this energy per charge, that's going to give us the voltage. So this expression here, KQ over R, that tells us the voltage at a given position. And this is actually a really important thing when we're coming to understand the electric field and Gauss's law. Now again, this might seem a bit counterintuitive. I guess we've all seen, you know, Ohm's law, V equals IR. That's usually how we think about voltage, right? It's a current, we've got a resistance, and we've got a voltage. This can be a bit strange. It's like we've just got a floating around charge here. What's up with the voltage here? Let's have a look at why it's important and useful to think about voltage as a concept like this. So do you guys remember last lecture we saw, you know, we've got the electric field lines, but we can also have equipotential lines. So for a point charge, they're just circles. Now, if we're another charge here, maybe we're thinking about we could be an electron. If we're an electron sitting over here, what these circles tell us is we can move around here without doing any work, without expending any energy. We can kind of circle around here. We're not getting closer or further away from that charge in the middle. We don't need to do any work. We're not going to gain or lose any energy. But even if we don't know what that other charge is, there's still a potential here. And that's actually what the voltage is. And that's why we call these lines equipotential lines, because they're lines that tell us where the potential is the same, where there's no potential difference. So these are all lines of constant voltage. So it's quite an interesting way to approach thinking about voltage. And as we're going to see, this idea actually really helps us to generalize these concepts when we're thinking about other forms of electric fields. Now, this equation in the top left, so the force, Coulomb's law, super important equation. Definitely you want to put a big old box around that equation in your notes. If you go and read up about Coulomb's law, maybe some textbooks, maybe read about it online, you might see Coulomb's law written down slightly differently. And part of why it's different is because we don't always have to use that K there, that Coulomb's constant. So sometimes you might see Coulomb's law written with this other constant instead of Coulomb's constant. So you might see it written with this, sometimes called the electric constant, this epsilon naught business here. And this is actually a more fundamental concept, a more fundamental number when it comes to thinking about the electric field, a more fundamental constant. So we can relate the electric constant to Coulomb's constant. They're just related like this. So Coulomb's constant is equal to 1 over 4 pi epsilon naught. And that epsilon naught, that's the electric constant. Now you might see Coulomb's law written like with the electric constant instead of the Coulomb's constant. Let's see which of these equations is Coulomb's law when we've just substituted in for the electric constant instead of Coulomb's constant. So we're just doing a bit of algebra with this. Remember, that's the force over there. What do we get when we do that substitution for the Coulomb constant? So we're just doing a bit of algebra with this, a bit of substitution. We know that the force, it's KQQ over R squared. So what's that equation going to look like if we substitute K is equal to 1 over 4 pi epsilon naught? Okay, so nobody's going for D. Looks like most people going for C. Now there's a few ways you can do it. You can either maybe start from the options and check them, or you can just substitute in for K and see what you get. And when you do that, so we're going to be dividing by the 4 pi epsilon naught. So that's going to give us option C over here. So very well done, everybody. Gave that question a go, especially if you got that, it's option C. So this is just another way that you might see Coulomb's law written down. So instead of the Coulomb constant, you might see it written down with this 4 pi epsilon naught r here. Now this is where it gets a bit interesting, because we start with our force law, and then suddenly we've got this 4 pi r squared business turning up in our force law. What's going on with that? This is really the line of reasoning that Gauss was following to develop a law to explain electric fields in general. So let's have a think about this question here. We've got this 4 pi r squared popping up here. Which of these geometric concepts does this 4 pi r squared correspond to? So if you're not sure about this one, maybe there's some that you can rule out because you recognize that there's something else. Maybe have a chat with the people around you, see what they think. Try and figure out which of these corresponds to that 4 pi r squared. Okay, let's see what everybody thinks for this one. What a geometric quantity does 4 pi r squared correspond to? Okay, so some people think it could be all of them. Looks like most people are going for D. So this is actually the correct option. So it actually corresponds to the surface area of a sphere. So very well done, everybody, with that one. So this is a bit surprising, right? We were thinking about the force acting on a charge, and suddenly we've got to think about the surface area of a sphere. So what's going on here? Figuring this out was really the key insight that helped Gauss develop a way to describe electric fields in a very unified way. So an approach which we can use to describe any electric field that we like. So let's take a look at the big picture here. Let's see what's going on with this surface area of a sphere business. So we've got our big old charge over here, and we've got these electric field lines coming out from it. Now the electric field lines, they tell us where a positive test charge will go. So I take my charge, put it down over here, I know it's going to go this way. And what Gauss realized is if we think about an area which surrounds this central charge, that really helps us to describe what's going on with these electric field lines. But not just any area. What we want is an area which always intersects the electric field lines at right angles. So every time a field line's coming through, we want a surface which is going to intersect each field line at 90 degrees. It's going to be orthogonal to it. So the field lines are coming off in all directions. So for a point charge, what that surface is a sphere. So that's where we get the surface area of a sphere. So I think it's really beautiful bit of geometry here that Gauss used to describe this electric field. So whatever distribution we have for our charge, all we need to do is follow this recipe. First of all, where do the electric field lines go? And we can do that by following where positive test charges go. And then for every field line, just put a surface which intersects at right angles and build that up. And that's going to give us the area that we need to think about. And what this allows us to do is to describe any shape electric field that we like. So let's see how this applies for our point charge, how we can describe the electric field in terms of the area. So if we go back to our force equation, I've just written the force equation there, so force is equal to QQ divided by, but instead of 4 pi r squared epsilon naught, I've just written as area times epsilon naught, where that area is the surface area of a sphere. Now remember that the electric field, it's always the force per charge. So we're just thinking about what the electric field is due to the enclosed charge. That's the relationship between force and electric field. So based on these two pieces of the puzzle, which of these two options are we going to get for the electric field due to our point charge. So this question might seem a bit tricky, but it's actually just some really simple algebra. We're just starting from that force there. We're just dividing by little q and seeing what we're going to get there. So it's actually just some very simple algebra to try. Okay, very good to see those responses coming in. Let's see what everybody thinks for this one. Which of these is the electric field in terms of our area? What do we reckon here? Okay, so looks like most people going for option A there. So we start with our force, we divide that by the little q, and what do we get here? Option A. So just q divided by epsilon naught times the area. So very well done everybody with that question, especially if you got that it's option A. Now this is actually a really important equation because it tells us what the electric field is for a charge, but it's not specific to how that charge is arranged. It's not specific to a point charge. And this equation is really what Gauss's law is telling us. So if you're writing along in your notes, you want to put a big old box around this equation, really important equation. This equation is what Gauss's law is telling us. So very well done everybody with that question. What's so important about this equation is it allows us to write down what the electric field is for any distribution of charge, not just a point charge. As an example, let's see how this works for the example of a capacitor that we saw a couple of weeks ago. So previously we looked at capacitors. We could work out the charge based on the voltage that we're putting across the capacitor, but we're kind of thinking about the capacitor as like a sort of a singular component. We weren't thinking about too much what was going inside. What this equation allows us to do is really think about the physics of what's going on inside that capacitor. So let's take a look at this example. Let's see how this works. Now I've got this picture over here. I've just done a kind of slightly expanded picture of a capacitor. So we have the two metal plates here. I've just kind of moved them apart a bit so we can see what's going on inside. In reality, they're going to be much, much closer. And I've just put it this way because I kind of like to have the electric field lines going this way. So this is the positive side. So our electric field lines, they're all going up here. Now we can use this arrangement of electric field lines and Gauss's law to figure out everything that we need that's going on with this capacitor. So if we think about an area here, this is the area which intersects the field lines at right angles. So all these field lines are going in the same direction. And if we draw little right angles here, the surface we're going to get is just a square. That's going to be our area. And this is the area which encloses that charge. So this is the area we need to be thinking about for Gauss's law. Now that we've got the area, Gauss's law is really simple to write down. It's just the charge divided by epsilon naught times the area. And there's none of this 4 pi business because we're not thinking about the area of a sphere. We're just thinking about the area of this square here. So just however big your capacitor plate is, that's what our area is. And our Q there, that's not the charge on a proton or something like that. It's just however much charge is on the capacitor. So it's actually a really elegant, really simple way to write down what the electric field is. Now you might say, well, hang on, this doesn't depend on the distance that we are from the charge. And that might seem a bit counterintuitive because we might instinctively think, okay, well, if we're right close over here to the plate, it's got to be a stronger field. And if we're further away, it's got to be not so strong. But if we look at what happens, if we move this imaginary area up and down, it always intersects the field lines in the same way. Because we're thinking about a uniform electric field, and between these two plates, we have a uniform electric field. So the field lines, they don't spread out as we get further away. So we don't need to, in this equation, worry about the distance that we are from the plate. So this is a complete description of the electric field here inside our two plates. Now again with this, a bit like on that first slide, we can't say straight away what the force is in this region, because we're only thinking about this charge here. And if someone said, well, what is the force, at this point over here? We don't know, because there's no other charge there. And we can only tell you what the force is if there's two charges, because the force is what happens between charges. So if we want to think about the force, we need to bring in a little charge over here. So it could be an electron, could be a proton, doesn't really matter what it is, just a little point charge over here. And once we know that we've got a charge there, then it's quite easy to write down the force. So the force, it's just the electric field multiplied by the charge. So we now have the force acting on our point charge when it's sitting in a uniform electric field. Now suppose we don't like our charge sitting just here. Maybe we want to move it towards this plate, or we want to move it over there. So we know that there's a force acting on the charge, and if we want to move something against a force through a distance, we're going to need to do some work. We're going to need some energy to do that. So let's have a think about how much work we're going to need to do. So we know what that force is. It's just QQ over epsilon naught A. How much work are we going to need to do to move a charge Q a distance d in that field? Now, again, with this question, it might seem kind of tricky. There's quite a lot of variables going on all over the place, and there's those epsilon naughts. But remember, work, it's always force times a distance. And we know what the force is. It's just QQ over epsilon naught A. And we're just exerting that force over a distance that we're calling d. So even though it might look quite tricky, it's actually quite a simple one to figure out. So see what you get for the work there. See which of those options is the amount of work we need to do to move a charge. Okay, let's take a look at the responses. Let's see what everybody thinks for this one. Okay, nobody's going for A. Maybe some people thinking it could be B or C. Looks like most people going for D. Now, this does look a bit formidable. We've got lots of variables all over here and these epsilon naughts, but it's actually a really simple question when you break it down. So we know what the force is. It's just this. And work is force times distance. So we're just multiplying this by distance. And when we do that, what do we get here? Q times D, which one is it? Here we go. So we've just multiplied by the distance. That's how much work we're going to do. So very well done, everybody who got that. It's option D, okay? Because it can be a bit of a scary looking question, but I think when you give it a go, it's not that bad, right? So this is how much work we need to do to move that charge around in a uniform electric field. Let's see how this fits into that puzzle that we're putting together. So maybe, our charge is over here and we want to move it this distance d, or maybe we want to move it the other direction. The amount of work we're going to need to do, or the amount of work that's going to be done by the charge, we just take this force and we multiply it by the distance. Now you might say, well, hang on, that seems kind of easier than last time when we were, having to integrate. Do you guys remember when we had to do the integral to work out how much work we needed? Okay, so we are actually doing an integral here to get from the force to the energy. But if we look at what our force is, our force doesn't depend on the distance. Our force is just a constant. So at any point between these two plates, the force acting on this charge, it's the same. It doesn't vary. So if you like, you can put this force in an integral and integrate it with respect to distance. But because the force is the same, that's just going to be the same as multiplying it by the distance. So it makes our life a bit easier. So this is the energy of a charge at a particular point in a uniform field. So very well done, everybody who works that one out. Really important result. Now, for the last piece of the puzzle for the lecture today, we just need to think about this area over here. So we know what the energy of a charge is at a particular location. let's think what the voltage is at a particular location. So we know what the energy is. Which one of these options corresponds to the voltage at that particular point? This is another kind of question that might seem a bit tricky, might seem a bit formidable, lots of variables all over the place. Maybe voltage, we used to, voltage is equal to IR, but this seems a bit different. But it's actually really simple when you give it a go. So we know what the energy is. We know voltage is just energy per charge. So we're just looking for that energy divided by charge. Which one of those options is going to give us the voltage? Okay, let's see what everybody thinks for this one. What's the voltage inside our electric field? Okay, so some people think it could be D. Looks like most people going for B. So we just need to start from the energy, and then we just divide out that little Q there, and what do we get? Option B. Okay, so it might look a bit formidable, might look a bit scary, but it's really not so bad once you give it a go. So very well done, everybody, with that question. This is the voltage at a particular distance within a uniform electric field. So very well done, everybody who got that one figured out. So for the last slide for today, let's put this voltage back into our puzzle, complete the picture, and see what we have going on here. So here's our kind of puzzle that we've been putting together the whole lecture. So we saw that's the energy, and then the voltage, it's just the energy per charge. Okay, so we just divide out that little Q, and we get this for the voltage. So Q epsilon naught A multiplied by the distance. So I love that there's the kind of symmetries in how these quantities are related. So if we look at the force per charge gives us the field. If we look at the energy per charge gives us the voltage. If we look at the force and integrate it over distance, we get the energy. And this is my favorite bit. If we look at the field and we integrate it over distance, wow, what do we get? The voltage. I just think that's brilliant. I love that. So I really love the symmetry of this situation. So this is really the framework that we get from Gauss's law, which enables us to deal with any distribution of charge. It doesn't matter if the charge is uniform. We just need to think how the charge is distributed, what the surface is, and that allows us to figure out all the concepts that we need. Now, this semester, we're only going to be thinking about radial fields and uniform fields, because the symmetry of that situation makes figuring out what the areas are much more straightforward. If we're thinking about more complicated distributions of charges, we have to follow where those electric field lines go and build the surface around that. Now, if you're doing physics, you're going to learn how to do that with a bit of vector calculus. You've got all that to look forward to. But this semester, we're going to be thinking about these two examples, but the principle is exactly the same, the relationship between the force, the field, the energy, and the voltage. Now, another very important point to make about these equations here. Hopefully today, we've got some understanding of where these equations have come from and how they relate. It's super important that you now get the practice in and try and solve these equations. So the way the questions normally go is we have, all but one of these numbers, and you can solve for what the other number is. So make sure that you get plenty of practice with these questions. They get so much easier with just a bit of practice. So we're going to have plenty of practice putting in the numbers with these questions, okay? Just another few kind of points to make. So next lecture, we're going to keep on thinking about fields, but we're going to be thinking about magnetic fields. So that's going to be really exciting. On Wednesday morning, we're going to be in the lab. We've got a really fun lab for everybody. I think you guys are really going to like it. And just a reminder, tomorrow afternoon, we're back in the workshop. So workshops back on tomorrow afternoon. Plenty of practice with these kind of questions. Really important that you put the work in, get that practice in. And there's a really good challenge question I think you guys are all going to like, okay? So excellent work today with all these questions. That's really great work figuring out Gauss's law. Hope you guys all have a great afternoon, and I'll see you guys all tomorrow.